Hi, I'm Howie Goldstein, and this is FC Level 1, Scrambling and 10b Encoding and Decoding. Remember to use the question comment box. Let's go ahead and start. The module topics here will be ordered sets, the idea of scrambling and all that implies, the idea of 8-bit, 10-bit encoding and decoding, and what I call the chicken and the egg, which hopefully we'll have fun with. Here's our fiber channel level diagram, and now we're on FC Level 1. And again, it's in FC Level 1 that performs the 8-bit, 10-bit encoding and decoding, the keeping track of what I'll call in-band control through the use of ordered sets. There are different ordered sets that exist in Fibre Channel. And we'll talk about link control in a point-to-point link environment, and later we'll at least talk a little bit about loop control and what happens in Level 1 if I'm dealing with an arbitrated loop. Fibre Channel has a series of control called ordered sets. And there are several transmission words that are used for control function. It's called an ordered set because there are bytes that occur in a certain order. Ordered sets are a set of 4 characters with a defined order and a defined starting character. All ordered sets begin with a special 10-bit character that is outside of an 8-bit data space. And when you think about it, if we have data that we're encoding, and we're encoding them 1 byte at a time, where I'm dealing with an 8-bit byte, the largest 8-bit combination would be 0 through 255. Well, if I'm going to have 10 bits, then 10 bits would be 1024. Am I going to need all 1024 combinations? No, I'm only going to need 255 of them, which means that I have 10-bit combinations that I don't have to use to represent data, that I can use to represent something else. And again, that something else is an ordered set. Ordered sets are used for different things. For example, a starter frame delimiter. The starter frame delimiter is a signal, or ordered set, that tells the receive side that he's about to see the contents of a frame coming in next. Better get ready to buffer that information so that you can decide what to do with that frame. We also have end of frame delimiters. Here's the end of frame. You've already received the CRC, the cyclical redundancy check, and we're at the end of the frame. We can use ordered sets to represent flow control. For example, there's the READY, which says that I'm giving you a credit. I'm letting you know about an empty buffer. Or an idle, which we saw was used when there's nothing better to send. There are ordered sets that are used to control the link and other low-level control kinds of functions. Everything that moves in Fibre Channel moves as a transmission word. 40 bits after 8-bit, 10-bit encoding. We move things 4 bytes at a time in Fibre Channel. The ordered sets will begin with a special character. Data words begin with an encoded data character. So if the first byte of 4 is not a special character, then I'm dealing with the data word. If the first byte of 4 is a special character, then I'm dealing with an ordered set. There are some 10-bit combinations that are just invalid. And if we see that on the link, we can identify it as an invalid word and indicate an error. There are 3 categories of ordered sets: frame delimiters, what's called a primitive signal and what's called a primitive sequence. In a primitive signal, if I see it or hear it, then it has a meaning. You might consider a primitive signal to be ugh. That's really primitive. If I'm dealing with a primitive sequence, then I need to see at least 3 of them in a row. If I can recognize 3 signals in a row, then I've satisfied my primitive sequence definition, and I'll act on it. An example of a primitive sequence, how about That'll take on more technical meaning as we move along. But that was a sequence of signals, and I need to be able to recognize at least 3 of them. All ordered sets begin with what's called the K28.5 special character. Again, it's a special 10-bit combination, not seen in a data space. If I see that in the first byte of a word, then I know I'm dealing with an ordered set. Which special character will depend upon the bit rate we're supporting. From an FC1 point of view, there are 3 basic functions. Encoding and decoding. All the information is going to be transmitted and encoded from 8 bits to 10, and when we receive it, it'll go from 10 bits to 8. We provide a unique transmission word for signaling and control. That's that first byte, that K28.5 character. And we can also use ordered sets to implement low-level control, like initializing the link or resetting the link if there was a problem. When I'm dealing with frame content, there is a process called frame scrambling. What frame scrambling does is reduce the probability of long strings of repeated characters. And let me just say, again, when we're dealing with the electrical environment, if I see a set of repeating strings of characters, what ends up happening is there's a resonance that occurs electrically, which can cause a loss of integrity in terms of the data stream. Frame data words are XORed with a seed value that causes us to scramble the information such that the repeating pattern disappears. We'll scramble the data on the transmit side. We'll unscramble the data on the receive side of a link. And again, we follow the same process with the same seed value. What I show here is the idea of frame scrambling. Again, I've got a 32-bit word. It gets scrambled into another 32-bit word. Remember, scrambling is not 10b encoding. That's something else again. This just shows, given a word or a series of words in a fiber channel frame, that scrambling has the effect of getting rid of repeating patterns. Notice here I had zeros followed by zeros followed by zeros, and the result of scrambling says I've gotten rid of those repeating patterns. And here we see the transmit data path. I have the first 4 bytes. I have a CRC generator that is constantly being updated until the last byte. Notice that I'm multiplexing that information and scrambling it. And then once that information is scrambled, it becomes 8-bit, 10-bit encoded. Again, the scrambling problem is something different than the problem addressed by 8-bit, 10-bit encoding, and out we go with the data stream. We also see the receive side. Again, the serial data stream comes in, we decode it, we unscramble it, or descramble, and then if we have a CRC, we put that away. We check it up against the CRC that we've been creating to make sure that things didn't change in the data stream, and now we have the transmission word that was part of the frame we were moving. Notice that we do not scramble control information, ordered sets. So we don't descramble it either. We 8b, 10b encode and decode everything. The reason for 8-bit, 10-bit encoding and decoding is, number one, we want to make sure that we provide sufficient clocking information so that we can recover the clock on the received side. Now here's what I mean. When I had parallel SCSI bus, one of the interfaces was the clock. And like a drum, the clock pulse gives us the timing as to when we should look at the data. When I'm looking at serial transfer, I take my synchronization from the data itself. And what I can tell is when there's a bit shift from a 0 to a 1 or a 1 to a 0, that's my opportunity to synchronize. Hey, I know that bit shift is occurring, therefore this must be a new bit. I can recover my clock. What 8b, 10b encoding does is ensure that we're going to have a bit shift every once in a while within a transmission word so that I don't get out of synchronization. We also, with 8b, 10b encoding, ensure a 50% duty cycle with no DC component. This is the idea of making sure that we're balanced over time in terms of the number of zeros or the number of ones that have been placed on the link, headed towards the receive side. And the reason why we 8-bit, 10-bit encode is so that we have enough information in the 10-bit space to be able to provide some special characters that doesn't appear as a part of the data stream that can be used to identify ordered sets for in-band control. A fiber channel 40 bits will always begin with a K28.5. We'll explain that nomenclature in a little bit. That indicates we're dealing with an ordered set. You know why it's called the special K character? Well, it's a serial technology. I know, you're groaning. Okay. It's just my attempt at humor. As far as the 8b, 10b is concerned, again, there are 256 separate decimal numbers. We don't need all 1023 of the bits to represent the data. And the reasons for 8b, 10b encoding was clock recovery, DC balance, and the generation of special characters, and the ability to be able to detect a problem in the data stream. The mapping is actually done with two logic blocks, a 5b, 6b encoder and a 3b, 4b encoder. And by the way, SAS, SATA, Ethernet, PCI Express, they all use 8b, 10b encoding, and it was invented by IBM in 1983. It's used by Fibre Channel and, as I said, other technologies as well. Here we see the 8b, 10b encoding space. Let's take an example. Let's say we use the example Baker Charlie, and I hit enter. Well, turns out Baker Charlie is not a character that we're going to be able to use to get back into balance, but it does meet our other requirements. And what are they? Well, a Baker is a 1011, and a Charlie is a 1100 in binary. The way we create the notation is, number one, it's a data character, not a special character. We take the upper 3 bits, 101, and we convert that to decimal, and we put it on the right side of the dot. We take the lower 5 bits, convert that to decimal, and put it to the left side of the dot. So from a notation point of view, This would be a dog 28.5 character. It doesn't really matter what the notation is. All of that is implemented in the hardware. The only time you'll see that notation is if we're dealing with a fiber channel analyzer. But what is important here is the 5b 6b encoder decoder and the 3b 4b encoder decoder. We take the upper 3 bits and we encode it to 4. And the result in this case is a 1010. We take the lower 5 bits and we feed it into the 5b 6b encoder. And in this example, we only have one result. So regardless of whether the current running disparity is negative or positive, for this character, we're always going to use the same data stream. And notice that I never have a situation where I'm using all ones or I'm using all zeros. Notice that I always am going to have a bit shift in the data stream generated. That way I can maintain my clocking. Let's use a different example. Fox Baker. Enter. All right, in this example, again, it's a dog 27.7. We take the lower 5 bits and we feed it into an encoder. And in this example, I'm either going to have a 110110 or I'm going to have a 001001. Notice that in the 4B, I'll either have all zeros and a 1 or all ones and a 0. Now, in this case, I'm generating 2 different data streams. And I'll use one if the current running disparity is negative, meaning there's too many zeros out there, or I'll use this if the current running disparity is 1 heavy. Now, although I'm not dealing with a higher count of ones versus zeros, I am changing the arrangement as to how the bits move across the environment. Let's take a look at dog. Enter. Again, the same thing happens in regards to the bit rate, or the bits. But if we look at the results of the encoders, notice that there are 2 possible results. One, if the running disparity is positive, and one if it's negative. In terms of the 4-bit encoder, we always use the same. But notice now that if our current running disparity is 0 heavy, notice that in this case is 1, 2, 3, 4, 5, 6. I'm sorry, there was an extra one here. And here we have more zeros than ones. This is an opportunity to be able to come back into balance. So there are 2 possibilities. The data stream that goes out depends upon whether the running disparity is negative or positive. So that gives you all of the examples. Here we see what I call the chicken and the egg. Think of those eggs as words, data words, of a frame. And I guess it would be FC2 that is the chicken. Remember, FC2 generates the frame and then goes down to level 1 for the next step. Now we take those eggs and we surround them with delimiters, the start of frame and the end of frame. Those are separate eggs, special eggs, called ordered sets. The start of frame delimiter begins the frame and the end of frame ends it. Starting and ending delimiters. Now we have what needs to be transmitted. We take those eggs and we take 4 of them. Remember, information moves 1 word at a time. Each of those eggs actually represent 4 bytes, which is 1 word. And now we scramble those eggs. Notice we do not scramble the ordered set, but we do 10b encode each of those characters, each of those words. And once we've 10b encoded, then off they go. moving down the serial link to the receive side. Again, we have the remaining portion of the eggs. We scramble them, except for the ordered set of end of frame. We 8-bit, 10-bit encode everything, and there they go, down the link. So it's an act of making a set of transmission words that have been scrambled or not scrambled. We 8-bit, 10-bit encode everything, and we move things down to FC0 for signal transmission. That, in essence, is the life cycle of what we're doing. Next, we have a quiz. So go and download the quiz, and good luck with the quiz. And remember, we not only have the quiz questions, but we have a section that has the answers with it as well, so you can check yourself. Again, if you've got questions, use the question comment box. Thanks for joining us. We'll see you on the next module.